everyone. Good evening. As Sir said, that these are the most important steps that we actually perform while we are doing statistical analysis. And borrowing from that and from my own experience, I'm going to take a stepwise manner on hypothesis testing. I'm going to take a stepwise approach. So what I'll be doing is that I will be teaching you hypothesis testing the way we are taught as PSM students, so that we can cover all the basic work, we can cover all the basic concepts, and I hope it helps. I would really appreciate if everybody could keep up the participation as everybody has done in our research lecture. So here's presenting the screen. Please let me know if the screen is visible to everybody.
Yes.
Yes, it is.
Yes.
Okay. So welcome to your next session, hypothesis testing. So one of the things that we do, or the most important thing that we do is while we are performing a statistical analysis, is we draw inferences. We draw the meaning of whatever we have done, what is the data that is in front of us. But the data that we have in front of us is not from the entire population. It is from a sample. You have a target population. From that, you draw a sample. Now, what you have to find out is that whether this population that you have selected, how closely it is represented by the sample that you have selected. So you have certain parameters in your population while you have certain estimates in your sample. How closely these estimates from this sample will resemble the parameters in the population, that is what a statistical inference is going to tell you. And one of the ways to infer your data is hypothesis testing, or the most important way to infer your data is hypothesis testing. Usually, hypothesis testing will be done in an interventional study, in an experimental study, or in a correlational study. Descriptive studies generally will have a research question. They wouldn't generally have a hypothesis. So the process of using the sample estimates to draw the conclusions about the value of population parameters, that is what we will be doing when we will be testing the hypothesis. But before that, we have to understand what are the sample estimates and what are the population parameters. So this slide is just to give you or to make you comfortable with the symbols that you will be coming across while you do your literature search or literature review. So for sample, usually when we are saying that we are measuring a proportion, so let's say this proportion of the population will be suffering from this disease, the symbol that we use will be a small p, and for population, the symbol that we use will be pi. For mean, this is the symbol that we use, and for population, this is the symbol that we use, a mu. And similarly, we have the symbols for standard deviation and for correlation. I will just leave this slide here. The idea is that the sample population that you will be drawing, because it's impossible and it's absolutely unnecessary to actually test the parameter of the entire population. It is not feasible, whether we are speaking economically or whether we are speaking in terms of the time that it is going to take to conduct a research. But it is possible to actually draw a meaningful sample from this population and to reach from here to here. Now, when we are reaching from here to here, first we have to infer this particular part. That is the estimates of the sample. What do they mean? What do we want to know from these samples? And then we will go towards the next step. That is whether the inference that we have drawn from this particular data set, it can be generalized to the entire population or not. So coming to the process of research, which is pretty basic and we all know it because we've all done it, we will be formulating a research problem. We will do an extensive literature survey. We will then develop a hypothesis on the basis of our literature survey. So will obviously select the study design, and we will basically, after your literature survey, you will come to know that this is what I want to find out. Now you will have a layman question like maybe this particular drug, you are testing a new drug and you want to say that this particular drug is better than the other drug that already exists. For example, if we are talking about COVID, whether plasma therapy is better than no therapy at all, or whether plasma therapy is better than, let's say, tocilizumab that we give. So that will form our hypothesis. Our hypothesis is essentially a scientific, or as you will say, it converts your whatever question you have in your layman language in a statistical question. Now when I say that it converts into a statistical question, what I mean is that now it can be tested. Now it has certain, or it has all the requirements that will be there for testing it, that will be there for applying a statistical test of significance to it. After developing the hypothesis, what do you want to test? Then, as Amir sir said, you will be preparing the research design. You will be determining the sample size that will be required to actually test this hypothesis. You will collect the data, execute the project, you will analyze the data, and then you will be performing the hypothesis testing. After hypothesis testing, you will be generalizing the interpretations, and you will be finding out what this means, what your research study actually means, and then you will be preparing the report and actually interpreting the result of the report. Before making a hypothesis, we should know what are the elements that go into a hypothesis. So hypothesis should essentially contain one independent variable and one dependent variable. I'm pretty sure that everybody is already aware of these terms. If anybody is not, please stop me and let me know if I need to explain any further. Essentially, a dependent variable will be the response that you get, and an independent variable will be the stimulus that you give. So the aim of hypothesis testing will be to see the relationship between these two. That is whether the predictor variable actually is predicting about the dependent variable or not. So if we look at this little baby, his hypothesis is that he will cry hysterically and that will get him another cookie. Anybody wants to take a guess that what will be the predictor and what will be the dependent variable in this? I think it's so simple that nobody wants to actually take a guess. Okay, so the anybody wants to go?
Cookie is a dependent variable.
Okay, getting the cookie is the dependent variable, yes. And crying will be the independent variable. So we can substitute this with any amount of studies that we have done. Crying hysterically is the intervention that the person is going to give. This is the stimulus, and getting the cookie is the result that the person is expecting. So, having cleared that of our path, the hypothesis, since we PSM people or community medicine or public health people love the definitions. So let's see the definition of hypothesis. The term hypothesis actually has Greek origin, which comes from the word hypothenia, which means to propose, and cis means a condition or state. So you're proposing a condition or a state. The condition or state can be anything depending on your research question and your literature review. So hypothesis in simple terms means a mere assumption or some supposition to be proved or disproved. It has to be either tested for its approval or its disapproval, that whether this is true or false. These are the tentative answers to the research problem that we are looking at. Now, these are the steps in hypothesis testing that we will be looking at. The first step that we have to do in hypothesis testing is essentially formulate what we call a null hypothesis and an alternative hypothesis. We will be taking up these steps eventually in this presentation. I will just walk you through all the steps first. After forming the null hypothesis and the alternative hypothesis, we will be setting up a suitable level of significance, what we also know as alpha or beta. Then we will be determining the test statistic. After determining the test statistic or the p-value, we will be looking for the critical region of the p-value. Then we will be actually performing the test and we will be computing for the value of the test statistic. And after we have all these values, after we have performed the test, we will be making the decision on the basis of our results. Coming to step one, so we will be firstly stating the null hypothesis and the alternative hypothesis. I'm pretty sure that we are already aware of these terms, but still to give you a refresher, A null hypothesis is basically something that will tell you that either the sample parameter, that the mean that you are saying is equal to the population mean, or the null hypothesis can be that this mean is equal to that mean. It really depends on your research question, that what you are trying to do. So, for example, if in a particular study you're testing two drugs, or you're testing a new vaccine, for example, we are taking Covaxin or Covishield, and we want to say that the mean antibody levels that were generated in the two populations who received Covishield or Covaxin were not different, or we want to say that they were equal. So then the null hypothesis, we want to say that Covishield is better than Covaxin. Then the null hypothesis will be that Covishield, the mean is equal, the first mean, that is the mean in the population of Covishield, is actually equal to the mean in the population of Covaxin. So this will be your null hypothesis. Alternative hypothesis generally goes with your research question, that is the question that you want to test. But it really, as I said, it really is very contextual. It depends on the research question that you're saying. Now, alternative hypothesis can be formed depending on whether you want to perform a one-tailed test or a two-tailed test. A two-tailed test generally will tell you that one statistic is not equal to the other statistic. It does not tell you whether your sample estimate that you're testing, whether it is a mean, a median, mode, or whatever you have calculated, that it is not equal to the other statistic that you're proposing. It does not tell you whether it is greater or smaller than the other statistic. But when you're testing for one tail test, when you're performing a one tail test, it gives you a direction. It gives your test a direction that either your sample is the sample estimate is smaller than or larger than the other statistic that you're proposing. For example, for Covishield, if I want to say that, as we said, that Covishield is better than Covaxin, our null hypothesis will be that the mean antibody levels in the two were equal. Alternative hypothesis, if I'm performing a two-tailed test, will be that they were not equal. And if my research question, but coming to my research question, then I will be choosing a one-tailed test, that I will be saying that the mean of antibodies in the population that received Covishield will be greater than the mean of Covaxin. So that is all about null hypothesis and alternative hypothesis. So null hypothesis is essentially an assumption that we hold as true until we have sufficient statistical evidence to conclude otherwise, or we have enough statistical evidence to actually reject it. So the symbol that we use is H naught for null hypothesis. If a population mean is equal to the hypothesized mean, then the null hypothesis can be written as this. Alternative hypothesis is negation of null hypothesis and is denoted by HA. If null hypothesis is given as H naught, mu equals to mu naught, then the alternative hypothesis will be given like this. That is, mu is not equal to mu naught. Can somebody please tell me whether this is a two-tailed test or a one-tailed test here?
Two tail.
Two-tailed test. Two-tailed test.
Thank you. And these will be the one-tailed versions of the same, depending really on what we want to test, which direction we are actually looking at. So we have a non-directional or a two-tailed test, and we have a directional or a one-tailed test. Non-directional is the assertion of one value different from the other, that is two-sided or not equal to, and the direction of the relationship is not predicted. So we will only know whether this proposed statistic is equal to the other statistic or not, or whether the observed statistic is not equal to the proposed statistic or not. We will never know the direction. But when we are usually performing a one-tailed statistic, we will have the direction, that is the direction of relationship will be predicted. So we have determined the null hypothesis and the alternative hypothesis. Now we will be setting up a suitable level of significance. I know we already know all of the meanings of alpha and sorry. Okay, I thought that was a question. So now we will be moving on to the next step, which is setting up the suitable level of significance. So before understanding before setting up the suitable level of significance, let us understand the terms which are coming here in play. That is the alpha and the beta, or the type 1 or the type 2 error. So usually this is the condition. There is an actual situation where, and this actual situation can be that either your null hypothesis is true or your null hypothesis is false. The decision that you have arrived at, that you either do not reject the null hypothesis or you reject the null hypothesis. If your decision is congruent with the actual situation, that is when the null hypothesis is true and you have not rejected it, that is a correct decision. Or if the null hypothesis was false and you have rejected the null hypothesis, then your decision is correct. But there can be other situations. That is, the null hypothesis was false, but you still failed to reject it. This will be type B error or type 2 error, which we usually say failing to reject the null hypothesis when the null hypothesis is not true or when the null hypothesis is false. Alpha error is failing to that alpha error is rejecting the null hypothesis when in fact the null hypothesis is true. So alpha is the type 1 error. It gives you a false positive conclusion. Again, how is it false positive? We have concluded positively by rejecting the null hypothesis, but it is a false positive because the null hypothesis was actually true. So rejecting the null hypothesis when it is true or when the null hypothesis is wrongly rejected. The example for this type of error is if the researcher concludes that there is a difference in the effect of the two drugs tested when there is actually no difference. So the null hypothesis was that there is no difference. Mu one was equal to mu naught. What we have done after testing the hypothesis, what we realized is that mu one was not equal to mu naught. So we actually falsely rejected the true null hypothesis. In this case, we will be getting what we call as type 1 error. So type 1 error will actually, how do we protect ourselves from this type 1 error is by setting up a level of significance. Then we choose alpha. Usually, we all know that alpha is taken to be at the level of 0.05. And unless and until you have a reason to change that, we already go for 0.05. Another commonly used value for alpha is 0.01. What alpha really means is that it considerably reduces your chances of rejecting your null hypothesis or accepting your null hypothesis, when it is actually true. So it reduces your chance of making a false positive decision. The level of significance is a measure in percentage of the risk that the researcher can reject a null hypothesis when it is true. So it is specified prior to the test performed, and the researcher can control the type 1 error by deciding before the test is performed, and usually it is 0.05. The level of significance, that is the type 1 error, will actually determine the critical values. Something that goes hand to hand with alpha or type 1 error is the type 2 error or beta, that is the power. It is the probability of rejecting the null hypothesis when it is false, or the probability of accepting the alternative hypothesis when it is true. So power is actually denoted by, when you come to power, it is denoted by 1 minus beta or 1 minus the type 2 error. It is analogous to the sensitivity of a diagnostic test, that is ability to detect a disease when it is present. Now, the p-value or the calculated probability is the probability of finding the observed or more extreme results when the null hypothesis of a study question is true. That is, the definition of extreme will depend on the hypothesis that is being tested. Now, this is the statistic, or this is the term that we are most comfortable with or most aware with. We usually say that if the level of alpha, now what we have to know is the relationship between p-value and alpha. That is, if p-value is lesser than alpha, then the null hypothesis is rejected. And this is usually what we aim for in our study. This is generally how the research questions are framed. So alpha is the threshold we decide before the start of the study that we measure p-value against. At alpha 5%, that means 5% of our result can be incorrect. That means 1 out of 20 times results may be wrong. P-value less than 5%, that is 0.05, will be required for the study results to be called statistically significant. If we take alpha at 1%, that would mean that the alpha would be 0.01, and there will be 1% chances, that is that chances will be reduced to be incorrect. That is only one out of 100 times we will be wrong, and then the p-value of less than 1% will be required for the results to be called statistically significant. So usually this is how we interpret the results. If the p-value is less than 0.05, then the results are statistically significant. If it is more than 0.05, then the results are not statistically significant. Statistically significant results essentially mean that there is sufficient evidence to reject the null hypothesis and accept the alternative hypothesis, and not statistically significant results means that there is insufficient evidence to reject the null hypothesis. This does not mean that we are accepting the null hypothesis. We are just stating that whatever sample size we have taken or whatever statistical analysis we have performed, it does not provide us with enough evidence to reject the null hypothesis. So we always fail to reject the null hypothesis. We never accept the null hypothesis. After that, we will move to the next step, that is determining the test statistic. So these type of flowcharts are extensively available in various textbooks of statistics or by a simple Google search also. It really depends on the type of data that you are using, the type of relationship that you want to find out, and the distribution of the data that you have. That is, for parametric test or for parametric data, you will have different kind of test that you will be performing. For non-parametric data set, you will be performing different kind of test. So if the type of data is categorical or nominal, you will be going for chi-square test. If the data is ordinal or higher, then you will be deciding what is the question. If the question essentially wants to measure the difference in means, then you will be determining what are the number of groups that you have. Are there two groups or are there more than two groups? If there are two groups, is the data paired? If the data is paired, then you will be going for paired t-test. If the data is not paired, then you will be going for students t-test. For more than two groups, you will be using ANOVA. Now, if the research question was wanting to find out the relation of variables, the related variables, then you will be seeing the number of measured variables. If the both variables are measured, then you will be going for Pearson correlation. If one variable is manipulated on measurement, then you will be going for linear regression. And if there is difference in related variables between groups, then also we will be going for ANCO. So after determining the test statistic, we will be determining the critical region. The critical value is the value that must be attained by the test statistic to be declared as significant. And the distribution of the test statistic is divided into area of rejection and area of acceptance. So this is the zone of acceptance where null hypothesis is not rejected or retained. And this is the zone of rejection when the null hypothesis is rejected. So essentially, if you just look at the graph, you can say that when you are rejecting your null hypothesis, that is whether when you have performed a robust, when your study design was good, when your sampling was good, and you have actually failed, you have actually managed to reject the null hypothesis, then the chances that your finding were actually chance findings are very low. So these basically whatever we have studied about one-tailed and two-tailed, this is a graphical representation of the same. For a two-tailed test, we will have area of rejection on both sides. For one-tailed test, depending on what kind of relationship we are looking at, we will have area of rejection depending on the relationship or the alternative hypothesis. For step 5 and 6, we will perform calculation, and on the basis of calculation, we will be drawing the conclusion. Uh, if the computed value of the test statistic falls in the rejection region or is not rejected if it or it is not rejected if it falls in the acceptance area. So in summary, you have to state the research question in terms of the statistical hypothesis. Then you have to decide on the appropriate test statistic for the hypothesis. You have to select the level of significance, which really depends on alpha that you're choosing. Generally, we take the value of 0.05. You have to determine the value of test statistic you must attain to be declared significant. That is the critical value, and which really will depend on the alpha that you're deciding on. And then you perform the calculation and draw and state the calculation. Obviously, you do not perform the calculation. There are various softwares that are there, and the one that we'll be using in this workshop is Tata. Um, so the I'm sorry. So this particular slide basically talks about confidence intervals. We already are aware about the p-value, but there is another and more emerging and more accepted way of presenting your presenting your inference, statistical inference, and that is the confidence interval. Why confidence interval are generally better than the p-value is because p-value usually gives you point estimates. P-value is dependent on point estimates, whereas confidence interval generally uh, gives you an interval estimate. When you are talking about p-value, when you are stating the p-value, you usually state it for a point estimate, that is the mean is this. But when you are presenting that same statistical inference in terms of confidence interval, you will be giving me a range. And when you will be giving me that range, the precision of the estimate that you're giving me actually increases, and the chances that the population parameter will be falling within that sample estimate also increases, because now we are presented with the range. So to indicate the precision of the point estimate, the confidence interval is used.
So, Dr. Shailaja, I'm going to stop you just there in the interest of time. And what we will do is probably we will record the session on the tests of hypothesis and share so that people can look at it. I'm sorry we are needing to do that, but I will also ask Dr. Amir to summarize this in a couple of lines, and we will share this session on hypothesis testing in a recorded mode at a later date.
Sure, sir.
Thank you, Dr. Shalja. It was a very good presentation, exact presentation, what it is actually the type 1, type 2 errors and all the things that you have tried to summarize here. I would just like the to tell that where to use statistical test and where not to use statistical test, because we have seen that whenever many times the researchers, the clinical researchers and other researchers, they come to us and say, please give a p-value. The question is just one, the demand is just one, I want a p-value. So let me throw a question here to the participants and ask them whether you can get a p-value or not, and if yes, then how. The objective is to find out the prevalence of peptic ulcer in above 60-year age group. Can I get a p-value? Yes or no?
No.
Can I get a p-value? Anybody else?
No. No.
No.
Okay.
Only if you have a hypothesized value to start with.
Obviously, if there's a comparator, just in this, no.
Some studies say that the prevalence of peptic ulcer in above 60-year age group is 25%. And I have to find out the prevalence of peptic ulcer in above 60 in my study.
If you're not comparing with any data, then the p-value is redundant probably.
Yeah.
Yeah. Anybody else? Yes or no? Can we get a p-value? Is there any way to get a p-value here? So I will go with what has been, what responses have come, which is very correct. Here we don't get a p-value. So when we don't have a comparator, when we don't have two groups to compare, there is no statistical test to be applied. And it should be explicitly mentioned in the objective that the intention is to compare. And that is what Dr. Shelja was referring to when she mentioned hypothesis testing. Hypothesis testing comes into picture only when there is a comparison. Without a comparison, you don't have hypothesis. So when she said, does the crying of the baby will lead to the baby getting something? So you can have one group of baby which is crying, another group of baby which is not crying, and then you'll see who gets and who does not do not get, and then you will compare, obviously, and then that's a hypothesis that you want to test. Or one group gets, one group does not get, and then you see backward who cried and who did not cry. Or if ethically it is permitted, you make somebody cry and then see whether they are getting or not, and you don't make the other group cry, the group of children cry, and then you see whether they have got or not. That is a random, is a controlled trial, that intervention study you can go if ethically it is permitted. So that is the thing, that if there is comparison, either way of randomized control trial, or before after study, or a case control study, or a comparative study, or a cohort study, wherever you have comparison, there will be a statistical test, there will be a hypothesis, the hypothesis testing. So that is one thing that is important, where to use statistical test, where not to use statistical test. uh, Another thing is about, yes,
Uh,
Dr. Richa, you want to ask
Yes.
them?
So in this question which you had asked, sir, if we have prevalence from the other studies, and we want to find out the prevalence in our particular group, then we can formulate a hypothesis that in comparison to the baseline prevalence, what is our, in that case, if we generate the comparative groups, in that case we can find out the p-value, but only depending upon our hypothesis. Am I right? Did I understand it right?
Okay, so we find out that in our study it is 40%, suppose, prevalence of peptic ulcer. So are you saying that we want to compare this with some other population?
Yes, if like you had mentioned, so like that the prevalences from other studies, how is it relevant? That is my question.
Yes. So we find that in other studies it is 25%, in one study I find, and in our, I want to find, the objective is to find out the prevalence of peptic ulcer in my population. So I find that it is 40% in my study. So the objective was to find out the prevalence of peptic ulcer in my population. So I found it 40%. There is no comparison here. Now, if you say that I want to change the objective, and I say I want to compare the prevalence of peptic ulcer in my population, in India, with that of Indonesia.
Okay.
So I will have to study Indonesian population also, and I will have to study Indian population also, because the other person who has done the study in Indonesia, we don't know what methods they have used, and so many things are there, many factors.
Mm.
So the difference may be because of those factors also, that we can't say when we are comparing it by the results of other studies. So whenever you want to compare, you should be on both the sides.
Mm.
You should be having control over this group also, you will be should be having some control over that group also. Then it is better that you say that we have found this in this, and we have found this in this, and we are comparing both. But
Okay.
if we are comparing our study result with somebody's result who has done something in their context and in their time frame and in their population and in their ways, it is difficult to compare it, because there are many factors that may be leading to that difference, not only the difference in the prevalence. So it is ideally not recommended to compare statistically just our prevalence with the prevalence of other studies. It is not recommended at all. If you want to compare, you do a prevalence study there, you do a prevalence study here, and then you frame the question: what is the difference in, is the prevalence of peptic ulcer different in the population of India compared to the population of Indonesia? And then we have to do a study in Indonesia and do a study in India, and we can compare these both. Is it all right, Dr. Icha?
Yeah, 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 yes, sir. Okay, thank you so much. Thank you.